year and a half, how long has it been here? 2 years, in building and generating computational models to study metabolic diseases, and really on generating personalized models. So what we wanted to do is really share how we implement these models in Julia, some of the advantages we're getting over MATLAB, which is what we previously used, and basically guide you through our pipeline for implementing these models and some of the tricks we've developed along the way. So a little bit of an overview of what we will be doing. We've implemented some short breaks, so approximately every 45 minutes we can take a bit of a break, go get coffee, have a bit of a walk around. For the first component, we really focus on first a bit of a quick introduction of what is systems biology, and then really implementing ODE systems in Julia, how to simulate them, how to visualize them, also including importing from SBML if you have an existing model. Following the break, we'll focus on parameter estimation, so how you can estimate parameters from data, regularization, so how you can improve the accuracy of the parameters you're estimating on limited data, and then move towards personalization. For much of this, we're going to use one of our in-house models called the Einthoven Diabetes Education Simulator, but the methods are generally transferable to any ODE system, even beyond systems biology. For the last component, we're going to focus on parameter identifiability analysis, both using the inbuilt Julia packages, but we've also implemented the profile likelihood approach that we've been using now for quite some years. And then finally, we're going to veer into slightly touch upon hybrid models. So how to really combine simple neural networks with the metabolic models that we are building to discover some unknown reactions and relationships. So that's a quick overview of what we'll be doing over the next 3 hours. I think I mentioned it to some people. So we have a lot of the code already uploaded in a GitHub repository. You can find the address up there at the top already. So that's where you will find examples of pre-implemented code. A bit of the general structure is I will discuss some of the theory, just so we're all on the same page, and explain some of the biology. And Max will then live code demonstrating how to implement these ODE systems, implement parameter estimation, and then we've also some exercises to try it out where Max and Michelle and myself and Natal will also be able to aid in any questions that you might have. So has everyone been able to find the address before I move on? So they're more the, oh, no problem. These are kind of the more general housekeeping, and then I will introduce in more detail who we actually are. Maybe I didn't organize this way. Are we good? We can go around with the link as well once we get onto the coding part of it. So yes, the organizers of the workshop are Natal van Riel, who's sitting here. He is Professor of Systems Biology and Metabolic Diseases and Head of the Computational Biology Group in the Department of Biomedical Engineering. So we're in the old building just across the road. My name is Shauna O'Donovan. I am in the same group, and my research line focuses on systems biology for the immune gut axis. And Max is a PhD candidate in our group, and his project is really focusing on hybrid modeling, and he's been using Julia exclusively for 2 years, so we hope to share some of our experiences and some of our tricks. We were not sure how many people we had, but I think we have a small enough group that we can potentially do a quick round of introductions, maybe your name, affiliation, or something that you want to share, just so we can have a bit more of a better understanding of the group and what you're interested in. So perhaps.
Yeah, sure. My name is Ahmed. I'm a postdoc at Nijmegen at Radboud. I'm doing similar things, but systems neuroscience, also using Julia to develop hybrid models and parameter estimation, but in the context of neuroscience.
Yeah. Maybe also Indira.
Well, I'm just a volunteer, master in sustainable energy technology, so super different topic, but yeah, I'm super interested to learn anything today. So
thanks also for your help today.
So my name is Manuel Stefer, and I'm a postdoc at Ulm University in the Department of Gene Therapy, and I'm also using Julia to generate different kind of models.
My name is Manuel. I'm a PhD student in Hungary, Semmelweis University. I do system biology, but I am in more base research size for investigating protein signaling pathways. Sometimes I use Julia for modeling, but I mainly use Python.
My name is Martin Ruppert. I'm a pharmacometrician and I work in for consultancy in Leiden.
Yep. Perhaps. Yeah, maybe. Yeah. Do a ring.
My name is Sebastian. I'm a PhD student at the University of Gothenburg. I also work in systems biology. I also develop some of the systems biology packages in Julia. So I'm responsible for one of the SBML importers. I'm responsible for the PTAB package for parameter estimations. This will be a very fun workshop to attend.
Yeah, I'm Paul Lang. I'm modeling and simulation engineer at Biosim, or Deep Origin as it's called now. And I'm the developer of SBML.
Hi, my name is Ivan. I'm a researcher and developer at InSysBio in systems biology and validated system. For pharmacology company, we use different tools. We use MATLAB, we use R and else, but currently we are mostly focused in Julia, so that's very exciting for me.
Yep.
Hello, my name is Steffen. I'm in Kyoto at the Institute for the Advanced Study of Human Biology. I'm a mathematician by training, but I mostly do modeling for developmental biology. Not system biology per se, but it seems to be good to know.
I don't know if you want to.
Yeah, so I'm Riel, and I'm a master student in the group, so I'll be here to help out with the questions you have.
Indeed, I took the liberty to introduce Natal.
Perfect.
I had prepared some Mentimeter questions, but I think since we've made a small group, we already pretty much covered how familiar are you with systems biology. Perhaps one question that could be useful. Oh, yes. I am old, I can't do technology. So not this one or the next one, but this one I think for us is quite interesting. Oh, maybe we have to go back to the instructions. We're very interested in kind of what you would like to learn from this workshop. Indeed, the code has been prepared to some extent, so there are limits, but if we can maybe tailor what we're showing you to address some of your questions. I guess we could shout them out, but maybe this is a socially safer way to do it. So if you want to, you don't have to. If you want to make some suggestions, you can go to menti.com or you can scan this QR code. I don't know if people, yep. We'll give it a couple of minutes. And then indeed the specific question is there anything specific you would like us to address in this workshop or focus on? Indeed, we've prepared some implementations of models and some sample code, but we have a lot of flexibility to focus on specific areas also, provided it's also within our knowledge. That could be a limitation. Nothing specific? Then I guess we can go on. So, this is a very general intro because I've never presented at a more programming conference, so I didn't know how much everyone would know about systems biology. I think the conclusion is quite a lot, but I think it could still be relevant to explain the specific system we study, so some of the models might make more sense. So the primary area we look at is human metabolism. It's orchestrated by this interplay between your liver, muscle, adipose tissue, and these all work together to maintain glycemic control. The main data that we look at is really these meal responses. So I think if there was some cookies or some snacks outside, what we look at is how long someone takes to regain control after consuming usually very high calorie meals. So this is what our data usually looks at. A nice thing to specify is it's usually very sparse. So this is from blood samples collected in humans. And really we have, this is actually quite a favorable time set where there's every 15 minutes. Usually we have every hour. And we try to build models to understand this data. So what will happen is, in a healthy person, they will respond quite quickly, and within 2 hours, they are back to normal. But in a less healthy person, they will take much longer. And this is primarily what our models aim to study. Why we call it systems biology is, and I guess all of you are in agreement as this is your area of research, you need to consider different parts of the body. You can't look at a reductionist approach of each individual tissue and organ. What we try to do is consider all the reactions that can influence the system, and to do so we use computational models. But I think this is always a bit of a risky question of what is a model. Yep. So systems biology can largely be broken into two main components, and we will touch on both today. So you have ones that focus really more on data and use machine learning algorithms. I think are there people have mentioned using hybrid models. Are there people using exclusively machine learning models? So using more data-driven approaches to identify these patterns from the data. Hello. But these are very data-heavy. So this can be quite a challenge in a field where you're relying on human samples, which I guess many of you also experience, which is potentially why you focus a lot on more bottom-up or knowledge-based approaches. And this is really taking the information that's known in literature, encoding them in the form of equations, and using this to study.
Sorry.
No problem.
I got horrifically lost.
It's just a brief introduction to the more biological topic anyway. It doesn't affect the Julia. And these models are based on knowledge, and they can be quite advantageous as they need much less data. However, their construction can take a lot of time. The advantage of having such a system is you can encode it in the form of equations, which will be converted to code. Apologies, I know this is MATLAB. These are old slides. But the key advantage of this is you can run it in a system. You can solve it very rapidly. You can simulate the system and understand what it's doing under different conditions. Another advantage is you might be able to infer reactions that you cannot directly measure. So this is a big advantage of using computational models, but we need to be able to implement them and solve them quickly. And I will give the caveat, as we're JuliaCon, this takes a very long time in MATLAB because I'm not very good at coding. So I think currently to solve this model and to fit it to data will take 10 minutes. And it's not a very big model, where Max will show you later the exact same model in Julia solves in seconds to minutes. Seconds, I think, yeah. So we'll see an example later on where we're actually going to fit this model to 700 people. And we'll be able to do it over the coffee break, where I tried to run some new simulations in MATLAB last night to generate figures, and it's still running, so they weren't included. So for the initial part, which is focusing on just the implementation of models in Julia, so ODE systems, which some of you might be quite familiar with, we're going to look at one of our in-house models, which is the Einthoven Diabetes Education Simulator. And this is a model that describes these key reactions surrounding glucose and insulin that maintain homeostasis in our body. It's quite a coarse-grained model, so it describes glucose appearing through the stomach and gut, or being released by the liver, and then taken up into other tissues as one lumped component. And it also describes the secretion of insulin and the degradation of insulin and how this insulin affects the reactions. So I think in total it has 5 equations and 4 equations. I thought I had 5. Oh, you've deleted the integrator. Yeah, there's one problematic equation, which is now gone. So there's 4 equations and 9 parameters. So it's quite a simple model. But I guess if we're implementing it, we also don't want a very complex model. And indeed, in the past, we've used it to study responses to different meals, and also for individualization, which we will specify more later. So I guess I will turn over to Max to go through the implementation. And I think I had some slides with equations, but I think Max also has them on the GitHub. So for the actual coding and implementation of the equations, they will be there. I guess before we start, are there any specific questions or requests?
I have a question about this model. How complex or simplified is it compared to other models?
So there are, if you go to literature and look for glucose-insulin models, I don't know how many you will find. I know we've worked with like easily 15 different ones. So they go from, later on in the program, we have a very simple model, which is called the minimum model, which is 2 equations, the most basic model you can have. And you have everything up to very detailed models that even go down to the cellular level, accounting for different transcription factors. This, I think, would still be considered quite a coarse-grained model. Indeed, it has only 9 kinetic parameters, and when we estimate them, we only estimate 3. So it's, I would say, still quite a coarse grained model. I think if we show this to a biologist, they probably wouldn't agree with what we're doing. But if you see from the figures, for us, it can fit the data quite well. So we are satisfied with this model. We've applied it now to 5,000 people. So we think it's sufficiently generalizable, but I would still consider it quite a small model compared to Michelle. I've just finished her thesis yesterday, and her model had 40 state variables and 75 kinetic parameters. And that's, I think, where Julia potentially comes to the fore, where I don't think she could have done her project if we were still using MATLAB. Because this model takes long enough to solve. Any other questions? Then I'll turn over to Max to actually do some coding, and I'll come back a bit later.
All right.
But yeah.
Can you open? Yeah. All right. Hi, I'm Max. I'm a PhD candidate here. As Sean already introduced me, I will set up the coding stuff. I think it should be on one of the screens. I can. Yep. I think if I end the slides, then slideshow. Can I do that? Yes. Awesome.
Yeah.
Then it should be here. Okay. I hope this is legible to everyone. So as you see, you already see 3 packages that we require. So if you want to set up your environment, please include these 3 packages. So we have static arrays, we have ordinary differential equation. You can equally use DifferentialEquations.jl if you want. It doesn't really matter. But right here, we're only going to use ordinary differential equations. The original Einthoven Diabetes Education Simulator is a delay differential equation. We're not going to look into that. If you're interested, the implementation is also on the GitHub if you want. It's not a very big change. Today I'll show how the ordinary differential equation implementation works, and yeah, I can kind of guide you through implementing it. Let me see. Yeah, so first some information about the repository. So you have we have a folder 1 implementation where we have different implementations of this Einthoven Diabetes Education Simulator. So we have the ODE implementation and we have the delay differential equation implementation. So they're already on there, but right now I'm just going to yeah, code it from scratch just to show you and explain kind of with every line of code what I'm doing and why how this model works. So we'll use the static arrays here because I've done a benchmarking. It's also on the GitHub repository, and that's actually the fastest implementation for this model. So what we're going to do is we'll start with a function. We can call it e-ODE, which is the ODE system, and we add the function signature that differential equations requires from us. All right, so we can deconstruct the state variables. So there are 4 state variables in the model, as Sean already explained. So the first state variable that we have is the glucose in the gut. I'll call it ggut here. I think it's how I call it in the other function. So that's represents the mass of glucose in the gut compartment. So it's the stomach and the intestines. We also have a state variable plasma glucose. We have plasma insulin, and we have insulin in a remote compartment. So make sure to assign them here. And we also have a lot of parameters. If you want, you can copy it from the original code file. So I'm just going to copy them from here because there are a lot of parameters here. Basically, we have 10 kinetic parameters, and we have some other parameters that take care of delays, that take care of basal values, make sure that it's in steady state. Or conversion stuff. So as I said, for example, this gut glucose is a glucose mass, while the other state variables represent concentrations. So we have to convert from mass to concentration in some way, and that's what some of these parameters will do. And I'll explain where that happens while we're writing the equations. So the gut glucose is actually one of the most complicated equations in our model, because it starts with it basically starts with the appearance of glucose in the gut, and we use a special function for that to represent the curve and curve of how this appears. This is a empirical function. I haven't got the citation here, but it's been validated before, and it kind of looks like a more delayed appearance of a delayed Gaussian curve. So the function looks like this. So we start with a sigma term. Then we have the first kinetic parameter to the power of sigma, and then to make sure that it's in, and then to make sure that the units are correct, we also have to multiply it by time, sigma minus 1. So now it's per minute in this case. So that's the first part of this equation, and then we have an exponential term in there because I said it looks like a Gaussian, and a Gaussian is usually something like this, and over here we also do it to the power of sigma. So now we have the shape of this curve. I said now we have a function that's in per second, so we need we also need a mass term, because the final equation is in milligram per sec or per minute in this case, or per time unit. So we also need to multiply by the amount of glucose in the meal in milligrams. So now we have the units correct, and we have the shape of this appearance term. We also need to this also needs to disappear into the plasma, and for that we just use a very simple linear or proportional term. So we can just do this. So that's the first equation. We have 3 more to go. So if you can't keep up or something, or if you have any questions, or if you can check the equations in the file as well.
If you can do the right date, I can give you directions to get on the I realize it's
Yeah.
Isn't the glucose an input to the model, or you could
So,
say?
So in this case, we model the glucose as well, but the only input that the model has is the mass of glucose in the meal. So it models the appearance of the glucose in the meal into the model. So you have models that also take the value of glucose from data as an input, as a forcing function. We don't do that in this model because it's a simulator, so we really want to be able to simulate a meal as well. Yeah. Yeah, it's also on the bottom there, JuliaCon 2024. Yeah, that's all right. So then we have plasma glucose, and plasma glucose, we typically like to split that up into different terms that represent different organs or different appearances or disappearances from different places in the body to make sure that it's also readable. So I will add a comment here just to show that we are working with plasma glucose. So the first term that we include is a liver term. So the liver produces glucose by itself, but that also might change over time a bit. So we have a parameter that we call EGPB, which stands for I think endogenous glucose production and basal value. So it's the basal endogenous glucose production.
You went to Philips Stadium.
Oh. Yeah, if you can help them, then all right. So this term basically controls that we have some glucose production always in this system, and this glucose production this is also decreased once you eat a meal. The liver starts to stop producing glucose, so that's what this term does. And We use a basal value GB, which is basically the glucose value at fasting, to make sure that this is 0 at the start of the system. Then we also have an influence by insulin on this in this case. So we also use a conversion factor beta. You can remove it as well because it has a value 1, but it's a bit of a, because we don't really know how this relates physiologically. We tend to use this in publications to make sure that there is a unit conversion, but the value that we take for this is 1, so you can also remove it if you want. And this one is dependent on the remote insulin. So we now have a liver term that basically has a basal production, so it has a steady state value, and as soon as you eat a meal, it starts to decrease, and as soon as the meal is taken up by your system and your blood glucose goes down again, then this liver will again be able to start producing glucose again. Then we also have the appearance from the gut, of course. So we have this K2G gut, but as I said before, this gut glucose is in milligrams per minute, or in milligrams, and we need to go to millimoles per liter. So what we do here is we have this basically the same term, this K2 times G gut, but we also have a unit conversion there. And this unit conversion depends on the body weight and the size of the individual that we model, and also has some conversion factors here. So we have this conversion factor F, which converts from milligrams to millimoles, and then we need per liter, so we need a volume of distribution. And we decided to make this dependent on body weight. Then we have glucose utilization. We have two terms for that. So we have an insulin independent term and an insulin dependent term. So we can start with the insulin independent term. I think these are dependent on the liver production as well, to make sure that it stays in steady state. And we have some other terms here that also make sure that the model remains in steady state as, after the meal is consumed. And this is a division term. I think there's like this. I hope I'm doing this correctly. And then we have, I think, this here. Yeah, you remember. The insulin dependent term. So we also, as soon as insulin appears in the body, then glucose starts to decrease. So we also want our model to be able to simulate that. We do that using what we call Michaelis-Menten kinetics, and we know that this response is a bit delayed, so we make it dependent on the remote insulin instead of the plasma insulin. So we again have this conversion of units, and we have the remote insulin, and then we have our Michaelis-Menten kinetics term. To make sure that this is. And also, if glucose is really high, then the kidneys start to filter out glucose from the blood. So we also have the term to account for that. And this is also dependent on the size of our compartment here. So we do that in here as well. And we have a specific cutoff value for that. So this is kind of a switch that makes sure that as soon as glucose goes above the value of 9 millimoles per liter, then the kidneys start to excrete glucose. So we account for that as well. And this is mainly so in healthy individuals. This typically doesn't happen so often, because glucose tends to stay quite low below the 9, but especially if we want to simulate people living with diabetes, then we need to account for this as well, because, yeah. All right, then we go to the last two equations. I'll promise to speed up a bit. So we have insulin.
Glucose together.
Hmm?
You need to put the glucose together.
Yeah, we'll do that at the end. That's
And
fine.
maybe just copy the insulin.
Yeah. All right, so the insulin, I will copy it here. So I'll just explain it a bit. So the insulin term there is simulated using what we call a PD controller. So the delay differential equation actually has a PID controller there, which is a concept from control engineering, and it allows us to control the plasma glucose in this system. We also have a liver uptake term that makes sure that it stays in steady state, and we have this transfer to the remote compartment. Yeah, so let's construct the glucose equation as well. So we have production by the liver, we have the appearance by the gut, and we have the utilization by insulin. So we have appearance and disappearance terms. And finally, we return this system. So we have a static array of our different terms. So we have gut, the GPL, the IPL, and the remote. And we add the function. So that's how a model basically looks in Julia. If you want to simulate the model, you also need parameter values. If you want the parameter values, they are in the IDAS-ODE file. So we have many parameters that we set to default values. And here we simulate a model that, we simulate an individual of 70 kilograms weight with a basal glucose value of 5 and a basal insulin value of 10. And we simulate a meal of 75,000 milligrams, so 75 grams of glucose. So in this case, if you are familiar with the differential equations package, then you can specify the parameters and the initial conditions, which we set to 0 and for the gut glucose and for the remote insulin, and we set to the basal values for plasma glucose and plasma insulin. And for this, we can simulate 240 minutes. So in this case, I still have the benchmark in here, but see, how did I call it? I call it solve. We can solve it here as well.
Maybe specify how to set up the ODE column.
Yeah, that's fine. Yeah, so these, so we put the function we called IDAS-ODE in there. We put the initial condition, the time span, and the parameters. We don't really have to specify the parameters right now. We can also specify the parameters while in the solve function. But I decided to do it here because then we can easily simulate it afterwards. So if you run this thing, it will probably compile my stuff, and then we can see what the model looks like. As soon as, yeah.
So this the Catalyst people in the back, like for this kind of model, could be implemented in Catalyst?
In principle, yes. You could implement this in a Catalyst. So the linear conversion terms and the Michaelis-Menten kinetics are quite easy to implement, I think. I think you might have a challenge with getting this gut appearance term right, because there's no real dependence in it. So I haven't tried it myself to implement it in Catalyst, but I think it should be able to.
You should be doing it. Well, you can add, for example, these also there to the actions and provide it special. It's probably easier to do your modeling tool in this case because this is not a transaction model.
Yeah. Right, and then you have the nice curves in here. So they represent the physiological values as well in there. So yeah, are there any other questions about this model, about how to simulate it, how to implement it? No, great. All right.
We have some options because we were unsure of what level to aim this at. So we have options of where to go next in terms of we have an extension of this model that introduces facts. So we have that as a almost exercise if people want to try it. But from the introduction, I get the impression that many people have a lot of experience with this package. So I don't know if okay or not. So we can allow some time to do the exercise, and indeed we have Michelle and Max to go around and help. Perhaps we can do that during the break because we've gone a little bit over time, and Max can quickly show that alternatively you can also implement these models directly from SBML. And while this model is quite small, and implementing it in ODEs is, even with the full explanation, took 15 minutes. Some models get very, very large, in which case it's not really practical to type them out. I think Michelle can testify to this. So it's also easy to implement them import them directly from SBML. So perhaps if you want to quickly show that.
Yeah, I don't know if I
use a different package.
I don't know if I have the package in here, but yeah.
Recompile, and then during the break, everyone else can maybe go get coffee if you're familiar with implementing ODEs, and if you want to stay and implement the Riel model. The equations are provided in the PDF. So you have the glucose-insulin components for free. And then you can add in fats. So if you want to try that, we can also give some guidance if you're unsure of what to do in implementing the ODE. Go back to Max.
Yeah. Oh, yeah. All right. So now I'll have to try to do it in the SBML. I haven't tried importing the SBML model yet, so I hope it works. So Paul, yeah. We have the two SBML import people here. So if something goes wrong, we have people to help. Yeah, but I haven't done I've done it with a different model, so I don't know if this this will work. I think this is EDES. We have the biomodels here. I think this is EDES, right? Yeah. So we have the model in biomodels database. So we have the SBML. The only question is it going to work? All right. Let's see. Can download it. All right. Yeah, I think I'll just try to do this in the break, and then we can.
I thought you'd already.
No.
Indeed, it should work because we've done it with other models. So for Michelle's model, which was a very large model, we did indeed download it from the biomodels database, imported it. It was a different model of immune signaling, and indeed, right out of the bag, it works. Which, as someone who usually has to type in the equations and find all the typos, it's amazing that that works. So maybe in view of time, we'll take a small break where indeed you can go get coffee, walk around. I think there's coffee there. If not, let one of us know because we haven't passed to the machines. And for those who want to work through the exercises, please feel free to just ask questions, or if you have any other questions. And if we come back at 10 a.m., we will start with parameter estimation, I think, which is potentially when things get a little bit more fun and interesting. So yeah, please feel free to walk around and ask questions. Oh, sorry. Yeah.
toch een beetje scary.
Although I think yes, it's
Je zegt dat gaan we even
her
spitsen.
dad works in Janssen and Janssen, so I think he's already
Dat
sorted
jij
out
dan
his
zo
internship.
zegt, nou, nou, succes.
Yeah.
Yeah.
But I think he mentioned his dad works for Janssen and Janssen anyway in the Netherlands, so he can get driven to yeah. Did the SBML work out? No.
No.
We just won't mention it.
No.
Yeah.
But no, we can say that we can
It does
mention
work, yeah.
It does work in Compasi.
It works in Compasi.
Yeah. No, it doesn't work in. No, it doesn't.
Really?
No.
My model works in Computational and
Yeah, sometimes it does, but.
that's interesting.
Okay. If you need it, that's there.
Where is the no video signal? Like this.
Don't know if everybody.
Oh. That works. Does that work?
Does it need to be turned back on again, or?
It works. So now I have to
yes.
share a screen, but I don't want to share my screen. Oh, this is now duplicated. It is duplicated now. I have to share, open in PowerPoint. That works. I can share the other screen. There we go. Yeah.
Yep. Okay. I think many of you heard me mention, so in the GitHub repository, the Computational Biology TUE, so that's our group's repository. You can also find some of our models there if you're interested. There is a second repository called JuliaCon Workshop, which is from a workshop we gave last September. And there we go through a lot of the methods we're describing here today, but using a more general Lacto-Volterra system example or simple enzyme kinetic examples. So if you're not up to scratch or as familiar with ODE systems and want to take a bit of time more to get into it at a less metabolism level, in these Jupyter notebooks you can also work through implementing ODEs, visualizing them, estimating the parameters, and doing all the analysis that we'll go through today, just on potentially, if you work in a different field, more intuitive models. I was wondering if anyone did try to implement the MIA model, if there's any outstanding questions. It's no problem if there's not. Indeed, I realized when putting it together, there's a lot more equations. I was like, oh, it's adding in 2 equations, but no, it's a bit bigger than I expected. And indeed, we did the coffee. So we spent a lot of time talking about implementing ODEs, but it's also thinking a bit about the structure of ODEs and what they are. So behind this figure, we see the equations, and the equations compose of really the reactions that can happen in a body. And in the case of human metabolism, we assume that these are fixed. So whether you're young, you're old, you're healthy, or you're sick, to some extent, glucose metabolism will physically stay the same. Your liver will produce it, your muscles will take it up. So the physical reactions will not change, but the models also contain kinetic parameters shown here in red. And in our application, modeling to study biological systems that change under different effects, but also interindividual variations, for us, the values of these kinetic parameters become very meaningful. So I guess the question is, how can you get kinetic parameters for your models? So indeed, people out there working with models, how would you find values for your kinetic parameters? If you were estimate them from data, indeed, is what we're going to show, but indeed the more traditional one is going to literature, which isn't fun. So during my own bachelor's degree, I made a model and I spent weeks looking for values estimated in rabbits and multiplying it by 10, because that's approximately what a human would be. And overall, the models don't really perform very well. So indeed, what we do, and indeed many people are doing, is, well, if you have data, we can use the data to try to infer values from these parameters, and this in part is achievable through the speed up in being able to solve and implement these algorithms in software and having the solvers to estimate these. So are people familiar with the concept of parameter estimation, or Just as a quick review, the idea basically is if we have data and we have a model, we can calculate the residuals, which is the difference between your current model simulation and your measured data. So you basically get some, if you think of linear regression, like a least squared method, where you can calculate the sum of squared errors and the sum of squared residuals. And you can put these into a solver, same way you would do for a linear regression system, an ODE system, any machine learning algorithm. And the key difference is rather than using a line, which you would do a linear regression, we use the differential equation. So the shapes are a bit more complex. So this is just a visualization of a fat model, where indeed you start at some initial guess, you calculate the residuals, iteratively you improve, and you should find a set of numerical values that will give you the best fit through your data. And this is an example from actually that model where we fitted to data before and after a very extreme calorie intervention. So these people were put on just 500 kilocalories a day for several weeks, which is very, very little. And you can see the blue curve is what we estimated before the intervention. The red curve is what we get when we fit the model to after the intervention. And then we could actually use these models to quantify what has changed metabolically. And I think a nice benefit of this is we found significant changes in parameter values that weren't found with traditional statistical methods. So I think this is where systems biology and ODE systems can be very powerful in studying biological systems. So I think Max is going to now go through how to implement the parameter estimation on the EDES model we've already implemented. You can also just copy the one from the file. And then we'll come back in 10-ish, maybe 15 minutes, and discuss some regularization and other strategies we can use to improve the values for the parameters that we get.
Close this one.
And indeed, if there's any questions, I think we're a small enough group, so just ask.
All right. Yeah, so the second part, parameter estimation. So we have quite some files in there. If you look at the two top ones here, so we have a least square optimization and so LSQ, and we have optimization. So I tried two packages for fitting these parameters. So we have nonlinear solve and optimization. Well, the upside of nonlinear solve is that it's a bit faster than the optimizations, but it doesn't have any. It doesn't work. Yeah, you cannot specify any bounds to your parameters, and because in this model it can get quite weird if you have unbounded parameters. We typically prefer to specify some weak bounds to our parameters while optimizing. And if you want to check how it can behave, then in the figures there's a really nice example of that of a weird behavior.
I think the key one also for many biological systems will be preventing your parameters from going negative. Because you will have certain assumptions in your equations that they should be, the direction of the reaction should be in a certain way. So indeed, unbounded parameters can become problematic if they begin to change sign, especially.
Yeah. Yeah. So these two files, so that this will require quite some more packages. In this case, I used a simple nonlinear solve, which is a very basic nonlinear solver to estimate parameters, but I typically use optimization. And there are some quite some things that we also do before actually optimizing or estimating the parameters. For that, we will need some other packages. So one of the examples is Quasi-Monte Carlo, which is a package that enables us to sample initial parameter values and to select the best ones to start optimizing from. So we can actually do global optimization. Yeah, so here we have the ODE model that's in there. And as you see, we have quite some parameters. And we're not going to estimate all of them because that would be unfeasible. So there are some parameters that we just fix to based on the data that we have. So we have body weight, basal glucose, and basal insulin that we typically set that to the basal glucose and basal insulin. We typically set that to the initial value of our data, just to make sure that it starts outright. And for example, this amount of glucose in the meal is also a parameter that we know beforehand because it's that we fix. So here I simulated some data before. So I added some random noise to a solution, and I think I can also visualize that, so I can quickly run some of this just to make sure that parameters. All right, so now we have a parameter vector, some initial conditions, some time, ODE problem, and where we do quite an easy optimization task. So we simulate data every 20 minutes, which is quite frequent in compared to the data we typically get. So we can solve the system, we simulate some data, calculate the mean and standard deviation, and then we can create a figure of this, which always takes a while. So this is quite nice data. If we would have this, we would be very happy. So we have data for glucose and insulin. We typically don't have data for glucose in the gut or insulin in the remote compartment because either we cannot measure them or they are not measured. They are typically not measured in the experiments. So here, this function is basically a way to combine the parameters that we fix and the parameters that we estimate. This is a thing I typically do. There are a lot of ways to do this, and this is just a preference, so it's not something I say you should do, but it's just something that helps me in estimating these parameters. But one of the important things to have when you estimate parameters is what we call a loss function. It takes in the parameters, it takes in some hyperparameters or other information that we need, and it solves the ODE problem and then compares the data to the solved ODE. One of the things I always do is I have this second argument where I just put everything in there, so I don't use any global variables, which is something you might experience in Julia that may be slow. So therefore I use it in this way that it doesn't depend on any values that I specify beforehand. And it returns the sum of squared errors between our solution and the insulin. And because glucose and insulin are on different scales, we also normalize them to make sure that the errors are kind of approximately related to the variation in the data. So I divide by the standard deviation in this case. Other options are divided by the maximum value or the mean value over time. It depends on what your preference is and what works very well. Here I also add an extra return thing. I return that just for visualization purposes, but that's not necessary here. So we also set some constants. So we estimate. So as I said, Shauna said we estimate 3. We can also sometimes estimate 4 if we're lucky with the data. We typically, if we go to individualization, we typically only estimate 3 because the fourth one sometimes works and sometimes doesn't. But if we estimate on average data, we can sometimes go for 4. In this case, we can do 4. So we will do 4 parameters. And in the individualization part, you'll see that we'll do 3 parameters. So the parameters that we estimate are K1, which is the appearance of glucose from the gut into the blood plasma, it's appearance into the gut. Then we have K5, which is the what we would call the insulin sensitivity of the tissue. So it controls how sensitive the tissue is to insulin. So if insulin increases, glucose decreases. How fast that happens is controlled by K5. Then we have K6, which is goes basically the other way around. So if glucose rises, how fast is insulin produced? And that also accounts for K8, which is also a parameter we can sometimes estimate, but on individualization we typically don't estimate that one. And K8 also is also a part of this PD controller, so it's the derivative part of the insulin response to glucose. So as glucose increases, insulin also increases, and this K8 basically controls how this first initial burst of insulin secretion. So we can create these create the constants. So we have some constants that we already set. We set them to default values that have been obtained once, and we start with making an initial guess. So in this case, I sample 10,000 initial parameter values, and I use some bounds to make sure that the samples are within a reasonable range for these parameters. And as a sampling strategy, we typically use Latin hypercube sampling because it allows us to sample from a very large part of the sampling space without doing a lot of samples. So we can very efficiently sample from the entire parameter space. In this case, I do 10,000, but well, it happens quite quickly. And then we compute the loss function on this on each of these initial guesses, and that we can do that as well. Doesn't take that long.
So how critical is it to do this multi-party sampling rather than just starting from random?
Yeah, so in our systems, we typically use this Latin hypercube sampling because the parameters are interpretable. We typically know the ranges that they have to be in, but also we also want to sample from the every parameter basically has its own function. So we really want to sample from as large as possible parameter space as possible in this case. And starting from random sampling, then we would need a lot more samples to cover this parameter space. Latin hypercube sampling is quite an efficient method to cover this parameter space without doing a lot of samples. So 10,000 is quite a lot here. I don't know how many you use in MATLAB.
In MATLAB, because of the time it took for doing individualization, I would use 5. I guess we got lucky. So indeed, to some extent with Julia, you could say, if I can do 10,000 this quickly, is it that much of an issue? But in MATLAB especially, we found the Latin hypercube allowed us to start from fewer initializations because we would cover the solution space more uniformly. Where with random sampling, there can be potentially, you don't cover the whole space and you need much more initializations to ensure you have the coverage.
Yeah, but if I have like a strong optimizer, I can sacrifice or I can start from random samples and then, so it's a bit more.
Yeah, it depends on the optimizer you use. So in this case, this initial sampling is part of the optimization pipeline that we typically use. So we start from a large Latin hypercube sample, and then we compute the loss and we select the best candidates based on that. So in this case, I just selected the best candidate from all these 10,000 samples. But yeah, typically we take about 10 or 50, depending on how stable the model is as well. Because if the model is very unstable, we typically need a bit more to make sure that we have enough parameter sets that converge. So in this case, we use the optimization package, and this package requires us to specify optimization function. And because the loss is made in a specific signature, so these parameters and these hyperparameters, we can just add it here. And we need to specify the way to do differentiation. In this case, I use forward diff because we have only 4 parameters, so we don't have like hundreds of parameters. So forward diff is one of the most efficient for that. And we add this optimization function to an optimization problem. So we can specify the function where we put the initial guess of the parameter in there, and all the hyperparameters that we need, and we add some bounds. So we add the same bounds as this Latin hypercube sampling. Sometimes we choose to change the bounds between the initial sampling and the final optimization, where in the final optimization we take them a bit more broad to make sure that our sampling doesn't bias the optimization too much. Right now we simulated data, so we know what the parameter values are, so that can be biased anyway, but we can specify the problem. In this case, I also made a callback to make a nice figure. So here I selected 4 optimizers, and I wanted to test what the different optimizers do and how long they take. So that's why I also made this callback here. This is just something you don't really need. But here I can initialize some predictions and the optimization algorithms. And but typically we can solve the optimization problem by calling the solve function, just like solving the differential equation on the optimization problem, and specifying the algorithm that we optimize. In this case, we do that for 4. And the first one typically takes a while, but then it just goes. There we go. That's all of them. And then we have a nice animation that we made of the different optimizations. So see how they fit the data. Well, this is a bit of a unfair figure because it looks like these particle swarm and nanometer optimizers take a lot longer, but they just take a lot more steps, while the steps individually are a lot faster. So it's a bit, but it's yeah. As I think if you run the code, you can make this figure yourself. You can also see if you select different initial candidates, you can see that sometimes one of the optimizers gets stuck in a local minimum.
So would you perhaps throw out to the audience, because I think from the intro we gathered that some people at least have a lot of experience with these methods. Do other people have preferred algorithms? I think everyone tends to get into a bit of a pipeline and then never change again. So is there anyone want to have preferred solver for such a problem, or?
We have found that usually if you have smaller models, then you can use an interior point Newton method with a full Hessian, and using multi-star optimizations usually works really well. If you have a larger model, again using a Newton trust region method, multi-star, and then have Newton Hessian approximation, it usually works really well. It's as long as you do many star guesses and have a good optimizer, it usually works really well.
I always had problems if the data is peaks. Like if these are peaks, then I usually need to template a loss function or something bad.
Yeah, we've experienced similar things, and indeed later we'll show we use a lot of tricks under regularization to try to force the model into more favorable parts of the solution space, and we find this to be very effective, at least with our data.
One thing that we also noticed that helps a lot is usually that if you have your parameters on the log 10 scale when you're doing the parameter estimation, because then the objective function gets more convex actually.
Did you have the parameters as?
And have them on the log scale, so instead of estimating as
log scale.
Oh yeah. Yeah. Sometimes works. Sometimes.
Yeah,
And it also prevents them from going negative.
Yeah, so
it's if you don't have bounded, if you want to use unbounded optimization, but you still want the parameters to not go negative, you can use a log scale. But if your parameters tend to go to 0, then it may become a bit unstable. But
then you start adding pipes and it's
yeah. Yeah, so there are many ways to optimize these systems. There's also you can also use Bayesian optimization using Turing. I decided to not include that because it's a completely different way of optimizing this system. And also in this model, it typically doesn't work very well. But for some models, it works quite well also. It allows you to also quantify uncertainty based on the data you have. I think the second part was about personalizing these optimizations.
First, I have the regularization.
Your first.
Personalize, as I mentioned, we have a lot of tricks. And actually, if you go into the code of our model, you would see in the papers we have a very long error function because we add a lot of these tricks, especially when we move towards the individualization. So if you think of the standard error calculation, indeed as Max introduced, we look at the sum of squared error between the model simulation and our data, and we optimize it. So this is the fit we get. And I think you would say, oh, this is quite acceptable. But as I mentioned before, the advantage of these models are we can simulate things we can't directly measure. So if we go in and we interrogate our model and we see what's happening in different compartments, no, this is why I shouldn't use animations. Oh, it's gone. There should be another bit down here. If we go in and look at what's happening inside the model, we can simulate glucose coming from the gut and things like endogenous glucose production. And what we found is that this endogenous glucose production has a very narrow dip. We expect this is where the initial, oh, this is strange, came from, that this is a very narrow dip, and we expected it to be a bit broader. And consequently, when we like to look at glucose from the gut, we noticed that only 25 grams of glucose is appearing. But these people receive 75 grams of glucose in a liquid drink. It's a very simple sugar and water solution. So there would be no reason why only 25 grams would appear, that there's fiber or anything that needs to break down. So we see that the model isn't quite finding the solution that we would like it to find. It's finding a good fit to the data, but not a biologically correct solution for us. So in this way, we begin to add things to our error function. So we give it some additional information, and we say, well, the area under the curve of the rate of glucose from the gut should be approximately equal to 75. And by adding this additional penalty, we get a different fit that is still acceptable, perhaps a bit higher here. But if we look again inside the model, we see that all of the glucose is appearing, or almost all of the glucose is appearing within 4 hours. So this is a biologically more correct fit than this one. And in this model, we have added a lot of additional regularization strategies. You mentioned indeed these peaks. Sometimes we also just add the peak again to the error function to really try to force it to find the solution that will capture this peak. We also have that the model doesn't always find the right steady state. If we simulate it for 10 hours, they don't go back down to the steady state. And therefore, we also add this to the penalty, that within a certain amount of time, it should return to the fasting. And this all comes from biological understanding of the system. But when we add this to the error function, it helps us with finding one solution, if perhaps there's many local minima, so this extra information can help. But also finding for us biologically more correct solutions. So this trick, I guess for lack of a better word, it's an engineering trick, is very useful when estimating parameters from data. Yep.
The 75 has no.
For this particular meal, they get 75 grams of glucose. So we know what's in the meal, and therefore we can add this. So this is because we know this about the system.
Yeah, but it still tries to get this AUC count as little as possible.
Or it's close to 75. So you see now it's gone to 74.66.
It's not squared, or something.
Yeah, it can explode.
Hmm?
It can explode. You just want to make AUC gut here as small as possible.
Not as small as possible. The difference between AUC gut and 75.
But there should be a squared, so
Yeah.
you can make the difference.
Well, yeah, sorry,
yeah.
it should be there.
Yeah.
This is also
That's
slightly, so this model was developed in MATLAB where I used LSQ-NOLIN that did the squaring in itself. So I apologize, this is a typo from when the model was originally developed. But we still apply the same regularization in Julia. And it's more, I think, if there's anything we can share about our experience with these models, this physiology-informed regularization can be hugely powerful if you're struggling to estimate parameters by allowing you to bring in other knowledge you have about the system. Even very simple things by saying, for example, this EGP now goes negative, which for this particular equation is possible, but maybe it isn't for your system. And you can add this information where you say that perhaps your fluxes shouldn't go negative. And again, it forces it into more favorable parts of the solution space without having to apply hard upper and lower bounds on parameter values, which may not work for all of your data. So in this way, you can guide your optimization towards solutions that are acceptable for you.
You can still interpret your confidence intervals for your remaining.
This is where we've run into a bit of a problem, and I'm afraid we haven't solved it in terms of the confidence intervals. Equally, we find it once we begin to rescale. So this error function is a combination of glucose and insulin, and as Max mentioned, we rescale to allow us to calculate it all together. And I also look towards Natal. We had an issue with how to relate this back to the chi-squared confidence intervals because we begin to manipulate our error function. Is it still meaningful? So I think that is something we still haven't, or at least I haven't solved, how to do this once you begin to manipulate your error function to this extent.
I think then you have to rely on sample and resample type of strategies like bootstrapping or something like that, you know, to get some estimate of confidence.
Yeah.
Sorry, wouldn't this particular problem be solved if this was an input to your model rather than a parameter that you're trying to estimate? Because it makes sense, or at least for me, from my understanding, it makes sense that glucose should be an input to the model. Right?
So the model does get that there's 75 grams of glucose, but when estimating the parameter, it finds a parameter that doesn't do it. So the easiest solution is to not take up all the glucose. Or at least this local minima doesn't take up the full amount of glucose due to that sigma, the exponential decay equation that Max showed you earlier. By choosing the K1 value of this equation to have a certain value, the area under the curve is smaller, but this gives it a good local minima. And basically by adding this to the error function, we give it a push out of that local minima because it's now penalized, so it disappears and it finds a different local minima. Other ways you could just fix K1 so it always appears, but I think next we're going to go on to individualization, and this parameter can be different between people. So we don't want to just fix it or apply harsh bounds because it might not work for everybody because due to physiological differences, this parameter is different between people.
It could also help in fitting it, right? So if it's direct data with variable inputs like this, it could also help, right?
Fixing it.
No, if it's different between people and then you see multiple values in your data, it can also drive you towards global optimism. Okay.
Like, do very briefly an interruption. Like, there is fresh coffee out there. I know you had your break already a little bit.
We have another one planned.
But yeah, do know that there's out there. So whenever you feel like that was a nice moment to wrap it up for a break, then it's out there.
I think then we'll quickly veer towards the personalization aspect, so we can do that more exercise and then also take another break. So indeed, much of what we've looked at is, as Max showed, this lovely data, although his was more frequently sampled, and that we can take it, and in this computer we can make a model. And this data looks nice, and as Max mentioned, we can estimate 4 parameters on this lovely average data. However, this is what our data most often looks like. And we see this variation between people, that there's huge differences, and we need our model to be able to estimate parameters for all of these people. But this is where the models can be very useful in allowing us to compare all these curves. So the shape and response of the glucose and insulin and plasma triglycerides tells us something about people's health. But how to go from these hairball of lines to a set of interpretable values can be very challenging for researchers in this field. The most common approach is to take the area under the curve, and that I really don't like because you lose all of your dynamic information. So this is where we've really been focusing on developing our models and our parameter estimation techniques. So the model that we implemented, the meal model, is something that was aimed to focus on quantifying this hairball of meal responses. So what we would then do is, using the parameter estimation and the regularization that I just introduced, we build a model for each person. And a key factor for us is that this model can somehow summarize the data. So Max mentioned some of our favorite parameters, which is K5, which is its insulin sensitivity, K6, which is a measure of how well your pancreas can produce insulin, and a new one that was in the meal model is K11, which says something about your liver fat and triglyceride metabolism. And when we build a model for each person, what we noticed, quite thankfully, is that as you moved around this parameter space, the shapes of the curves changed and increased. So you see as we move towards this low K11, especially this low K5, we begin to see this very high insulin, and for the low K11, this very high triglyceride, which is a sign that people are losing their metabolic control. So in this way, we see that the models can be very useful and parameterized in uncovering this data. These are older results that were done in MATLAB, and what I will say is it took days in my poor coding to get these personalized models generated. And this was for a small data set of just 200 people. The field is growing, so this is a recent study, or at this stage a bit older, from the UK, where they have this response for 1,000 individuals. And this is where you really see the limitation you hit if your model takes too long to solve. So this is kind of a question that I guess we will answer a little bit during the break, but how long would it take to generate 1,000 personalized models if 200 of them in MATLAB took 2 days, 3 days on my desktop? So I think the data is available in the GitHub repository. The code is also there, so there's some
Yeah, the data is not fully available.
Not fully
it's a
available.
subset of 50 people.
I thought you put the full 700. Max will do the full 700, so he will be able to concretely answer our question during the coffee break. But if you want to implement the parameter estimation techniques yourself, so you can ask us questions during the break, please do. There's a subset of 50 people in there, so you can test it, and you will also see it doesn't work for everybody.
Yeah, there are examples as well. There's also a file that does this already, and there's examples of model fits that don't work. And maybe you know the reason why it doesn't work. We know, but maybe you can find out.
Yeah. Yeah.
Mixed meal model because of mixed effects, or is it mixed
No,
meal?
this has been pointed out to me multiple times recently, and I think I need to change the name. Mixed meal refers to the fact that, so I showed you the glucose one with the 75 grams of glucose. That's what they call an oral glucose tolerance test. It's used clinically to diagnose diabetes, and it's just sugar and water. The mixed meal is sugar, water, fat.
Protein.
Yeah, oh, protein, yeah. No, sugar, yeah, protein, fat, and sugar together. So it's used in nutritional research to really challenge the system. And the advantage of it is by also pushing on the triglyceride response, you can really see differences in metabolic health earlier. So that it's not mixed effect, although we have implemented it with mixed effects parameter estimation. So we do have that also implemented if you're interested. Also as a way to check what's happening with populations. So sometimes you can have, if you're more interested in the population response rather than the individual, you can use mixed effects, treating the individual as the random effect. But indeed, I might need to change the name. Yep, I've had that multiple times actually in the last couple of weeks, so I do think I have to change the name of it. Because everyone thinks it's mixed effects.
Interesting.
Yeah. But we do have implementation of it, although...
Of which one?
The meal model. Or we have an implementation of it in monoliths, but we will shortly have an implementation in Pumas. There's a student working on it. So indeed, we will have an implementation of it in Pumas soon. Yeah, so do you have any other specific?
No, yeah, I can show the data, how it looks, but it's not very special, but it's in this folder. We have glucose and insulin and time points. So the challenge here, a bit of a challenge here is that the time points for insulin are different than time points for glucose because we're missing one. So then you also have to take into account that you have more data for glucose than for insulin. If you look at I think this one, predict individuals, then you can see how the individualization that I tried works. It's very simple. It doesn't contain any regularization, yeah, you can try it if you want. Yeah, and if you want to compare the fits, this is a bit difficult to see. I have to change it to light mode. See if this.
This is indeed when the bad local minima appears. You mentioned also peaks. This is something we see often with our model. That if one parameter gets too high relative to another, the model oscillates. Which is an excellent solution because it will go through every point, but it's not, again, the solution that we want. So this is where the regularization can be useful, where we can tell it, well, it shouldn't have more than 2 peaks. We know this biologically. And this will encourage it not to go into that solution, but to go into this solution. So yeah, we could also change our model, which we're working on, but this is an easy fix to avoid those parts of the solution space that lead to very unfavorable behavior.
Yeah.
Because that happens a lot. If Ka gets too high relative to K6,
yeah,
this happens. So, yeah.
Whenever you see it in a demo code, then I get a bit. Whenever I see the seed in a demonstration, then I think.
Oh, no, the seed is just for the initial sampling. It's not for anything else. You can change it if you want. This doesn't really.
The initial sampling.
Yeah, for the sampling of these 10,000 initial parameters. And it's just to make sure that the figure is reproducible. You can change the seed or remove it if you want. It doesn't really influence the.
I think with 10,000, I can't imagine it having a huge effect, considering we usually do it with 5 to 20.
It shows that it is very tricky.
Yeah, well, it's because what we do is we typically just simulate the model for a lot of individuals and then select the best candidates for optimization. So if you typically this is.
Does it have an effect, the seed, on this initialization for the software for one person?
No, but just for the sampling of the initial parameters. So this like a half cube sampling.
With 10,000, I can't imagine.
No, it doesn't have a huge
effect. So with 10,000, I think it's more of a practice that Max employs, but I think if you removed it, I wouldn't expect it in this model to have an effect.
Then again, 10,000 is
excessive.
Quite.
Yeah.
But it just shows that we can do it. As I mentioned, doing this in MATLAB with 5 or 20 initials really takes a long time, where we don't have the luxury of doing 10,000 there. Unless we have a lot of patience or we get access to a machine. So it does show that indeed the random sampling can allow you to get an equivalent coverage. I think indeed they mentioned this coffee, so if you want to work through the example that Max included, again, Max, myself, and Michelle will be here to answer questions, or if you want to take a 15-minute break, get some coffee, have a bit of a walk around, and we'll be back at 11, where we will look at identifiability, which I think is where a lot of this comes together when estimating parameters, and also where having a computationally efficient model can be very useful. And Max will also show some of his results in integrating small neural networks into these models to learn missing reactions and relations. So yeah, please feel free to, or if you have any questions, just. Yeah. is coming up, so there's lots of time for conversations, and indeed you can think of your meal responses. Just a quick check-in, if anyone was working on personalizing the model using the data provided, is there any questions there? Perhaps. Indeed, I understand that this gets a bit niche into our research area, so may not be of interest to everybody. I think this was kind of a not open, but a general question I posed in terms of how long would it take to generate 1,000 models. As I mentioned, I got 5 students to do this in MATLAB about this time last year, and across 5 laptops it took 3 days to do it. That could say something more about my coding than anything, because they used my model. So Max ran it over the break, and it took
4 minutes.
4 minutes.
But yeah, so this model is a larger model. So this is the mixed meal model. So it will also take a bit. So I think EDAS would be even faster. But I think this one is 13 equations.
So as we are at JuliaCon and we are somewhat emphasizing the benefit of using Julia in systems biology, I think for us this is what motivated us to make the transition. That the data sets were getting so large that we really couldn't, and the models are getting bigger, that it really wasn't sustainable for us to continue in MATLAB. I think in this next section we're looking more at identifiability analysis, and again another motivation for switching to Julia is Max will present some of his work and share his experiences with moving towards more hybrid models combining neural networks with ODEs. And I think this is particularly where we experience Julia shining. But a bit of moving towards identifiability analysis. And I thought I would share this classic Occam's razor, although I think I've seen an excellent tweet that said, what is it, all models are wrong and my models are atrocious, rather than all models are wrong but some models are useful. And it's this general idea that the simplest model is often the best solution. And why we highlight this is model selection. So Max mentioned before, and perhaps I should have shown this before, if you have a model with 9 parameters as we do in EDES, or in the meal model we have 25, it's not really feasible to estimate them all from data, especially the data we have, because it's very sparse. Once an hour, maybe once every half an hour, and we typically only have what we can measure in the plasma. So we don't have all the internal body states that we would like to be able to accurately estimate these parameters. So we have to select a subset. So this is a pipeline proposed by collaborators of ours at this stage a couple of years ago, which looks at identifying sensitivity analysis, so which parameters affect the model output the most, to identify a subset that you can then move towards and test all possible combinations. And this works well for small models, but not for larger models, even in Julia. So this is a newer pipeline that actually Michelle will show in a poster tomorrow, where we do the same steps, where we do this pre-selection using local and global sensitivity. And then we move towards a parameter selection procedure where we try to find the minimal parameter set that will allow us to describe our data well. So we use the ACCI information criteria to find a balance between the complexity of our model and the quality of our model fit to the data. And in this way, we can find a subset of parameters that we can estimate from the data. But this brings us towards what properties do we want these parameters to have if we want to interpret them for biological reasons. So indeed, throwing it out there, what is a key criteria for these parameter estimates, if we want to derive biological meaning out of them? Anybody? So the key component is that these parameters are identifiable. And that namely is, if we estimate a parameter from data, that we get a reasonably unique solution, and not just that a whole line of values can satisfy our equation. And this is what we call identifiability. And this allows us to be more certain in the value, especially if we want to say that this person is healthier and this person is less healthy based on our parameter estimates. We need to be somewhat certain that we're getting a solution that is in a minima. And I think there are a number of packages, and Max will go through some, pre-built in Julia that will assess structural identifiability. So they will look at your equations and tell you if these are structurally identifiable. We're always interested in data. So for many years, we've been using profile likelihood analysis. And how this works is if you have a set of parameters, let's say 4 that we estimated earlier, and we want to get an idea of if we are in a local minima, what we can do is use profile likelihood analysis, where we will fix one of our parameter values to its optimum, and we'll re-estimate the other 3. And then we can do that again. We can iteratively increase and re-estimate. And ideally, what we would like to see is that if we are in a local minimum, that the error will increase as we move away from our optimal value. This is what we would, and then indeed, I think you brought up this question about the confidence intervals and the thresholds. The definition of being identifiable is that it would meet this chi-squared threshold, which is calculated based on the degrees of freedom in your parameter estimation problem. And this relies on the fact that you have nested models because you fix one parameter and then you estimate the 3, so you have nested models. I will admit this is something we've abandoned a bit in our own research, where we more look at the profiles to see at least if we're in a bit of a local minima. But ideally, if you have an error function that is just a pure sum of squared errors, you can use this to calculate a confidence interval. And a parameter is deemed identifiable if it has a finite confidence interval, or at least this is what we found in the papers coming from the Rooij group. So this is, I think, for us, a fairly well-used paper. And these are examples of different profiles that were gotten for these 2 parameters. So are people familiar with this approach, or is this new for some people? I see indeed some agreements. So maybe indeed also for the newer people, if we were to look at this 2-dimensional profile, so if you look at the concave plot that it's decreasing, what would you say about the identifiability of this parameter? Yeah, so this is identifiable and the error value increases as you move away from it. If we move maybe towards case 1, where we see what they call this banana valley, what would you say about this parameter? Yeah, it's not identifiable, and actually this would be structurally not identifiable. So typically measuring more accurate data or maybe more measurements, more time points will not fix this problem. To fix this problem, you really need to measure something new or change your model. For B, this shape is going up at one end, but continuing in a line or a valley at the other end. So anyone have an idea of what this parameter would be?
It's one-sided.
Yep.
All is practical and non-identifiable.
Yeah, so this is what we consider practical non-identifiability, and this is to do with data. So typically this type of profile can often be remedied by just changing the data you're measuring, getting more data, better quality data, and then you can hopefully restore identifiability to your parameter. So these are the 3 main types of identifiability we look at. As in our own research, we're often more interested in fitting 2 data. For us, we just consider if it's not identifiable, it's a problem. I think some people just focus on structural identifiability in their model. So indeed, they appear. This is more a repetition to show that indeed you can remedy the situation by changing your data. So you can see here is a run initially where many of these profiles are flat lines. And indeed by introducing new data and changing the model and re-estimating, suddenly these profiles primarily become identifiable again. Except for this one, which still remains practically unidentifiable. So it is an important thing to consider when estimating parameters. However, a key challenge is if you look at this profile likelihood estimation I mentioned, which really involves re-estimating parameters over and over and over again, I think you can get the idea that this becomes computationally heavy. And I think my record for running PLA is 14 days. Because at a certain point you're afraid to terminate it because it might almost be done. And that was in MATLAB. So this again is where Julia can really help in terms of its efficiency. So I think you have some implementations also for this.
Yeah, so I first can mention some of the packages that we could work with if you want to implement this or want to do this in Julia. So there is a likelihood profiler package it does take a different approach. It doesn't recompute this estimation, but instead it proposes a different approach, which seems to be more efficient in computing these confidence bounds. My experience with that is when you change your loss function, these confidence bounds are not valid anymore, and it becomes very difficult to use that package. There's also structural identifiability, and that was a more analytic method where they try to see what is your data, what are your data inputs to your model, and if you have this data, can you actually estimate these parameters? And it doesn't necessarily look at practical identifiability. So in terms of computing identifiability analysis, initially for parameter selection, structural identifiability is nice because it can identify parameter sets, at least if your model is small enough, because we also tried it with Michel's model and it was a bit too large for structural identifiability to be able to identify a parameter set that was identifiable from the data. But for models like EDAS, that they might work quite well. But then again, profile likelihood tells us also something about practical identifiability. So that's something we implemented ourselves. And in MATLAB, we had some really nice automated time stepping as well to make sure that we don't do re-estimation too often. And in Julia, I just abandoned that because it's fast enough, so I can just re-estimate every parameter change. I think it's so the implementation I quickly did in this is in this file, so you can run it if you want. It should run. And what we typically do is, I think here we simulate some data as well. So we use it on the simulated data. I haven't tried it on this predict data set, but at least for this experiment. So we do kind of repeat the initial initial parameter estimation experiment, but then we provide an additional loss function for PLA that is kind of a wrapper around the original loss function, fixes one parameter, changes it a bit, and then re-estimates the others. So I set this up, and if you run this, you should hopefully get this figure out of it. And the orange dots represent the parameter values that we estimate, and they have the likelihood profiles there. And because we changed the objective function, because we scale it, the chi-square confidence bounds are not valid anymore. So what I typically just do is I add the 2 times the objective and 3 times the objective value, just kind of as a proxy for how much does it actually change with the parameter value there. So yeah, I think that's it for profile likelihood. If there are any questions about this. Yeah?
Have you considered adding this? So I mean, there's some packages that are similar with profile likelihood, but have you considered to add your work as maybe?
I have considered it. I haven't had the time, but I want to, I might do it in the future.
People would be very grateful for that, because I think this is where Julia is lacking a bit. Software, they have this adaptive stepping, which
yeah, we have the adaptive stepping. I have an implementation with adaptive stepping, but it's I have thought of some improvements, but if it's there, I can. If there's a need for it, I can try to work on that.
Yes. So the package you mentioned, like the profiler, was developed by my colleagues 7 years ago to prove kind of a paper we wrote and did it kind of hard to use in a practical sense. There is also a package, Practical Identifiability, now I think it implements this general thing to step through the profiler. I don't think it supports adaptive stepping, but I think in MATLAB we got used to using SimBiology, which implements many different algorithms. So, likelihood profiling, and now we are re-implementing it in Julia, and I'll speak about it in Julia. So,
yeah, indeed.
Thanks for for introducing this topic.
Yeah, well, indeed, I think we typically also don't use this. You haven't used SymBiology and MATLAB for doing this. We also have our own implementation.
Tal wrote something years ago that we've all been using since.
Yeah, so I think there was a question also from the back.
So when we decide whether it is identifiable or not,
We can go a little bit fuzzier. So at least if we can see a very pronounced local minima, we're reasonably satisfied. And a big advantage of doing this in Julia is previously, because it took so long to calculate, we would do this for the average data. And as Max pointed out earlier, often this average data is very smooth and very nice. So we were perhaps overly confident in our models. Oh, these are identifiable. When we get to individuals, their responses are very different. And with this sparse sampling, you might be missing a very crucial part of the dynamics. And for some individuals, it's not identifiable. You begin to get these very straight profiles coming back. So an advantage of being able to now calculate this so quickly in Julia is we can now calculate identifiability for every individual as we are calculating their models. And indeed, we see that in a not insignificant proportion of individuals, some of the parameters become unidentifiable. So Max mentioned this 4-parameter model, and for personalization we use 3. This is what motivated us to actually further decrease the model once we could calculate a fuzzy identifiability, or at least confirmation that we were in a local minima. If you have any ideas on how to get the thresholds out with our just crazy error functions or heavily modified error functions, we would be hugely appreciative, because currently we rely on sampling. I think Balázs in his most recent paper used this profile likely, or you mentioned.
You used likely profile.
But still, we weren't 100% sure if this is valid, considering how much we've changed our error function. So this, for us, is a big area where we would really appreciate some input, because currently we rely on sampling.
Just to be crystal, is it just the adaptive time step and the reason why you didn't use? I think there's the one that the likelihood profile, and there's another packaging profile likelihood.
Yes, profile likelihood.
Yeah, so there's 2 profile likelihood packages in Julia. Is it just the adaptive step in why you wrote your own?
No, it's also because we know how the code is not that complicated, and we had it in MATLAB, so we just decided to write it out ourselves, because we know we can compare it to our own implementation in MATLAB, which has been validated before. So yeah, it's also a convenience for us.
I think potentially you did this at the very
Yeah, I think I did this nearly 2 years ago.
Yeah.
So then.
So I'm not sure when those packages came out. I think we did like a cursory search for options that were out there, and then decided to just, as Max said, very quickly. I think it took an afternoon to implement our own. So.
And is it just for single profiles, or can you generate bivariate profiles as well?
We just run it for single. Indeed. Any more questions or comments? And indeed, the code is in GitHub, so if you want to try it on your own models or data, please feel free. Or indeed, maybe to compare it to the ones that are out there. I think, yeah, it's the same. We also have, I think we didn't include it here for time, but we also have packages that implement local and global sensitivity analysis. I'm not sure if they're in this one, but I think they're in the other GitHub repository.
No,
I thought they were.
There's a very old implementation that someone else made. So how made it? But
okay.
Yeah. So I'm still working on a new one, but that's.
Yeah. But also we'll show our emails again at the end. Contact us if you want any of these scripts. We're very happy to share them.
If they're not on GitHub, then we'll share them.
Yeah. The MATLAB ones are all there.
Yeah.
Can I go back to my?
Oh yeah, of course. Yeah.
So I guess quickly moving towards the end, and I think we alluded to this at the start. I started in this field about 10 years ago, and my experience was there was a big separation in systems biology. You did machine learning, or you did bottom-up modeling, and there wasn't a lot of crosstalk in between. And this is changing a lot, especially with the SciML packages. where we're really looking at more hybrid models. How can we combine machine learning with knowledge, allowing these models ideally to be trained with much fewer learning examples by reducing the solution space, but also by facilitating data integration and rapid model extension, where we can really put very simple universal approximators into our ODE, simultaneously train it by applying some type of symbolic regression, really recovering analytical formulas, and really rapidly extending our models. And I think this provides a lot of opportunity into the future. And this was actually the primary motivation to switching to Julia, because we didn't like ODEs in Python and we didn't like neural networks in MATLAB. And Julia solved all of our problems in one go. So this, I think, is where we use it most heavily. So Max has an implementation to show what additional packages are necessary in order to achieve this. And we have a very simple example that we have managed to implement. Maybe I'll let you describe it, as this is your work.
I don't know the plot on the right, but...
This is the original Bergman model from 1979.
All right.
So this is the original data. So maybe
Yeah.
I'll do this slide.
Yeah.
So we have a much simpler model. So you asked about model complexity. This is the Bergman glucose minimal model. And this describes what we saw previously in IDES in 4 equations and 9 kinetic parameters, in 2 equations and 3 kinetic parameters. And it's one of the earliest glucose-insulin models, developed in 1979, but it was developed for what they call an intravenous glucose tolerance test, where they inject a very high amount of glucose and observe the insulin response to this. So you see the glucose curve is different to the meals we looked at. It's a rapid rate of decay. And our data is typically meals. So for us, I think if you press there were some questions. So we want to be able to describe these meals, not the injection. So how can we modify the model? And there are, you saw in IDES, there's many very simple models that can describe the shape of appearance. But we saw this as a nice opportunity to see, can we learn the rate of appearance? So indeed, applying this very shallow, simple, I think Max can provide more specific details, into the glucose equation of the model, to learn this rate of glucose appearance from the meal using the regulatory effects of insulin. So I think you have a brief implementation of this.
Yeah, I have an implementation that kind of does the same. It's not an exact implementation, it's not an exact copy, it's also on different data. So this one is on the full and the entire predict subset, which contains a bit more weird individuals, which also makes do these weird things if we don't apply regularization. So this is actually one area where we have me and Shauna and Natal and another collaborator have a recent preprint on regularization of these hybrid models. So if you're interested, you can check out that. So that's where the figure actually is from. So in this case, what we did is we applied this regularization of constraining the area under the curve of this rate of appearance to match the glucose taken up, because we want this neural network to describe a kind of a biologically relevant, interpretable curve. So that's what we did, and we made sure that in that way we can fit this this data quite well. The glucose minimal model is made for intravenous tolerance tests, and this data is actually on a mixed meal, or the muffin from predict actually. So we really don't know how these additional fats interact with the glucose in the stomach and the gut to change the absorbance of glucose into the plasma. So what we did there is we applied this regularization to enable the neural network to fit this data and to estimate a curve of appearance. And a very similar neural network setup is also implemented in this, I think in the repository. The effect of regularization is a bit less pronounced there because the data is a bit smaller and there's less variation in the data. I think if you look at the curves for without regularization, you see that there are a couple of peaks, and there's this weird one that tries to that thinks glucose appears out of nowhere, and with slight regularization you can see that we have complete steady state that we learn. Because this is different data, it's not the same figure, but the idea is the same in this case. And if you want, you can check it out here. So we will need a bit more packages for that. So in this case, I decided to use simple chains, which is a very basic neural network package. It's made by Pumas, and the other implementation used Lux, but it's basically the same type of neural networks that we can use there. For this, we have an implementation of this neural network that we use, and we have implementation of the minimal model in here. So feel free to check it out, and if you have any questions, then
maybe for time you can go through this in a little bit more detail.
All right. Yeah, sure. All right. So we have the minimal model, and we add a regularized loss function. So in here, it's very simple regularization, where we just use the trapezoid rule to compute the area under the curve of this simulation. So it's a very rough area under the curve that we calculate here, because we only calculate it for the data time points here. And so it's not the exact implementation as I did it before, but it seems to work quite well.
But more so to getting the ODE and the neural network together, I think if
Yeah.
people are familiar with it, it can be nice to...
Yeah, the idea is that I typically write a function around the ODE, where I supply the neural network. In this case, I also supply the insulin interpolation, because that's how the model works. And we call the neural network from inside the ordinary differential equation to make sure that it works in that way. Typically tend to split my parameters up into ODE and neural network parameters using component arrays just to keep them separate. But yeah, that's also a matter of preference.
And how would you write the error function for this model?
Yeah, it's same as I would do it for the regular ODE. So we simulate, so we have a component array with ODE parameters, which are kept constant in this case, and neural network parameters, which are given by the parameters of this loss function. And we just solve the problem again. Here we also use the T5 optimizer, because we assume that it's not going to be very stiff. And this assumption is quite okay in this case. It sometimes goes stiff, but that also depends on the initialization you use. So we typically tend to do a lot of initializations, and then just, if it errors, then just skip it, because then it probably becomes unstable. And that's also implemented over here. So I think
First.
Yeah, so did you try more classical neural network regularizations like an L1 and L2 on the parameters? Because as I understand the regularization now, you basically punish the model to not blow up in a sense. Yeah,
so this blowing up, so what we see is that analyzing these parameters does not necessarily prevent the model from learning odd biological behavior. So it could equally learn oscillating patterns, which is really not what we want, with constraining the parameter sizes. So by using this, we make sure that it still retains the freedom to get to the curve that we want, but also doesn't do, also specifically gives us a curve that represents the biology here.
So it's basically trying to include your qualitative knowledge about the system into the regularization as an expert.
Yeah, but they need this constraining of parameters. It's also an effective way of regularizing the neural network in this system. I think I have a poster where I also, I think tomorrow during the post session, you can see my poster where we only do that and use that for a different purpose.
Quite effective. But in the preprint, we show this for multiple systems. Max shows this for multiple systems. So we start from simple Michaelis-Menten, this minimal model, and we show that adding this additional qualitative knowledge can be simple and powerful in terms of what comes out of the trained models. I think you also had a question.
I actually never implemented such things to make the question is very stupid. Here in this model, the neural network trains a 1D function, so T mapping to real number. So in principle, it's a fancy way of saying we could also just use any other interpolator in this particular case.
Yeah. So that's the system is called a universal differential equation, not because it's not necessarily means that we need a neural network. We could in principle use any universal approximator in this case. In this, we have just seen that neural networks tend to be really nice in how they are able to describe these types of curves.
I would expect that they're nice when it's higher dimensional.
Doesn't
are they also nice when it's like 1D to 1D?
Yeah, and typically we have small systems. I think they are what I observe is that they become nasty when you have when your actual system is 1D or 2D to 1 or 2D, and you're using a neural network that's that has higher dimensions. But if you make sure that your input and output relation is quite constrained to what is possible or what you know about the system, then they are they work quite well. Yeah.
In this one, the model parameters are also estimated.
In this one, the model parameters are not estimated.
But we have done it where parameters are also estimated.
Yeah, that's also in the poster.
So how do you then make the trade, or how does the model make the trade-off between structural, physiological parameters and the weights?
Yeah, so this is also an open, kind of an open question in the field, where we have only like approximate answers to that. So we have tried some examples in this case where we estimate model parameters together with neural networks, and as long as your neural network is a different subsystem to your model parameters, then this tends to work quite well, because the sensitivity of your neural network parameters is only, or is very limitedly related to the sensitivity of the other parameter there. So what you can see is that the neural network is only responsible for a part of the system, and it has a hard time compensating, for example, for structural or numerical errors in other parts of the system. So that's why this works quite well. But there's also the danger of that other parameters become unidentifiable because you're including a neural network. So it's also relevant to check that beforehand. I think one comment on that is it's hard to check identifiability of neural network parameters because we don't assume them to be identifiable from how neural networks work. But what we can do is we can check the other parameters' identifiability while giving the neural network the task to compensate, and then we can see how well we can do this.
And indeed, we're starting with relatively trivial examples. So the aim is to go on to where we really don't know the reaction, but initially we're starting where we already have some quite good models of these systems, so we can see how well the neural network can perform compared to those. But indeed, we've already seen that bringing in more data helps a lot. Yeah.
So how well does it compare if you just use a neural network, maybe it's a bit bigger, and removing the initial model? Can you try this?
For this model, I haven't tried it. I have tried it for a couple of systems, but what we see is that the data requirements become so high that your neural network easily overfits on the data. So it's also a balance. Like the main thing is that your model is a type of data that you include and give to your neural network as information.
If you can pull up some real responses.
Where from?
For the data, just to show it, because we haven't tried just a neural network, but previously we have experimented with pins, which is where we have a complete neural network and then we just add the model to the error function. Just any real response at all. Our data is so sparse.
Yeah.
The issue we have is it will go through all the data points, but between the data points,
you'll get something. You'll get something like this.
Not necessarily that. What we saw is it almost learns a step function. It doesn't learn a smooth curve. It learns to step. And because we always have the same time points, it's quite a good fit. So that's what I imagine would happen if we went in with just a neural network without supplying it with some additional information. And even with the pins, it had the model to check the error, but it's still between the actual data points that constrained it, it learned something very strange. But it's partially because our data is so sparse. I think it has been very successful in other fields, but our samples are, this is even a bit too nice for what we typically get for the mixed meals, which is about once an hour.
Yeah, I think it also depends what you want to do with the model in the end, right? Because if you have a black box neural network, then you get a better fit to the data, but then what?
Yeah, so our collaborators want explainability, and they want to use it to understand more about the system and differences between people. So, indeed, for our specific questions, this approach currently seems to show the most promise, but who knows when we get into more challenging data.
And you mentioned you looked into, or you're interested again to look at symbolic regression of these neural networks. Do you know if these, have you tried them, or do you know if these are already there to actually capture something that's meaningful?
It depends. So, if you for simple systems, they work quite well. What we do observe is if you have sparse data, then and if you have, but also if you, even in simple systems, you kind of need to know what your input and outputs are before you can confidently apply symbolic regression. So as soon as you apply other inputs, especially in biological systems, this doesn't work anymore because it learns these correlations, and because of these correlations, it doesn't know anymore what to learn. So there is a...
It learns a really good shape, but it doesn't mean anything. So if you look at our data, this is very highly correlated. And the symbolic regression just picks one of them. So some of the equations we've gotten out fit the data beautifully, but they're describing insulin secretion as a function of gut glucose because they correlate. But that's not quite what we want. So it's a problem we're currently tackling, how to apply symbolic regression with such highly correlated.
Yeah, I think it's an open challenge everywhere, so it's still,
Yeah.
Cool.
But this step function that you guys see, it doesn't really match with the trapezoid AST thing that you use as a penalty.
No, this is a different,
It was a different
implementation. So yeah, there you use a neural network to estimate the entire system, and you regularize the neural network output using a model. This is
or we found to get it to, you can get it to work well, but you have to supply data from features that we cannot measure. So I think Natal published it.
It's in a it's in a conference.
It's at a conference. There was a student, Erasmus student, who worked on this with Natal last year. You needed to supply a lot of information about glucose in the gut to get it. So this was a big issue, this glucose in the gut that we do not measure. So she found if she could supply this data using the model and a lot of it at the initial training, it learned something quite good. But that's not realistic for what we're getting from research projects or from clinic. We don't have this information about people. So we would then have to fit the model, infer rate of appearance of glucose from the gut, put that into the pin, and at that point, what does the pin add that the ODE model couldn't? So that's, for our very simple problems, we didn't find, or my opinion would be the pins don't add as much. But we have a lot of colleagues across the street who work on more PDE systems, and they've had big successes with the pins because of the computational time. As you've seen, we can fit 1,000 models in 4 minutes. So for us, computational time is no longer a big issue. So there wasn't a big advantage we found in switching to pins. This reintegration of the neural network and the ODE seem to better bring in this knowledge to constrain the system than pins did for us. And indeed, yeah, it wasn't just the area of the curve penalty. We really had to supply this full curve to the pin for it to start to learn anything that wasn't a step function. I'm not sure how they reported it in the paper.
Yeah, I think it's similar.
Yeah. Maybe in view of time, although I think we already veered to it, so our plan was for the last 15 minutes to have more of a discussion in terms of any open questions based on what we've been going through today, any points based on your own research you would like to bring in or discuss.
Just a curiosity. So when you train your UVs, did you have to do any specialized approaches in your training scheme? Like, did you have to run ADAM with VHS? Did you try different learning rate schedulers? Because
so my experience there is that it's kind of a trial and error for Adam. Learning rates, I typically set learning rates in terms of powers of 10 because individual learning rates don't really changing them very slightly doesn't necessarily improve the training there. But what really works for us, and I think also other groups have seen it, is that you really need to train multiple initializations, and then your learning rate influence kind of diminishes. As long as it's not too high, there's always an initialization for which the learning rate is appropriate, as long as it's not too large or not too small. So if you make it really small, it doesn't learn anything. And BFGS has a initial stopping conditions. So it's ending with BFGS also makes sure that if your learning rate is slightly too small, make sure that you have a valid stopping condition there. What does help there is to set an initial step norm for BFGS that is a bit smaller, because when you start with Adam, you already assume that you are in a better optimization range, or you're quite close to what you want. But if you then add BFGS, then sometimes the initial steps it takes are way too large, and your model becomes unstable. So constraining the initial step sizes of BFGS also helps in optimizing these systems.
Have you looked into SDEs or thought about it?
No, we in our group we typically don't really look at SDEs for these types of systems. I don't know if you have any experience with stochastic differential equations.
No. I think it could be very relevant to things in biology. There's obviously a lot of stuff going on, but typically we try to focus something. But a lot of what we've been doing is estimating parameters from data and their stochasticity. We don't really simulate very often, or at least I don't. There are some people in the group who use the models more for simulation and prediction and forecasting. So perhaps there it would be, but we're typically using it to estimate parameters from data, and then need the UDEs to learn terms from data. So we don't typically add stochasticity into the models.
And you don't assume that there is something random that's not captured in your states, or
no. Currently, no. I think it could be very relevant to include it, but a lot of our data is collected under really controlled conditions, and indeed there are definitely things that are affecting that we're not accounting for. We kind of assume these just get absorbed into parameters, but the data is collected under very controlled settings. So as much as possible, this stuff is controlled for. But as we move towards sensors, perhaps it could be very relevant to begin to have something in there.
Yeah, so for this UDE approach, you discussed earlier that it's kind of difficult to make sure that the neural network doesn't do too much and the ODE too little. I would assume that if that would be the problem, then common practice should be to just add the square of the neural network to the objective function as a regularization term to force that the neural network does as little as possible, potentially by weight, multiplied by weight, but that's not what is done normally.
It is an option. So you mean the parameters of the neural network, or the neural network output instead?
The output of the neural network.
So yeah, so it depends. So if because if we have quite some scales in this system here, so if you look at adding the output of the neural network, then you can also I think what we did here is if you look at the preprint, we also did something with regularizing the output of the neural network. There we constrained the output of the system to not become lower than 0, and thereby also constraining the output of the neural network.
I think it depends potentially on the problem, because the current one you're working on is combining insulin and glucose, and they're already on different scales. So potentially saying that the neural network is contributing too much is difficult. Potentially here, where it's all glucose, it might make sense, I think, potentially.
Yeah, and other options there are, what you could do is you could constrain your neural network by using a different activation function at the end, which is typically more stable than regularizing, and also computationally more efficient. So I think what I did in one of my other projects, where I actually wanted to learn modulation in systems, I used the hyperbolic tangent as the output of a neural network, and I multiplied it with a parameter that, and you can constrain that parameter, and thereby you can constrain the output of your neural network. It's the output size of your neural network.
I think indeed, in this example, it's really part of it. It's explaining almost one of the equations. So I think enforcing it to have a minimal effect might impact. We wanted to have a contribution, but indeed in those examples where it's part of one of the equations, indeed Max has constrained it in the past.
Yeah, it depends on whether you know it has a contribution or whether you want to learn whether it has a contribution. So it also depends on the problem that you are facing.
And actually the second question this time, so you incorporated the area under the curve into the objective function, right? But thinking about how people have measured the area under the curve, probably the way they've done it is they measure the time course with some time points, right? So the area calculating the area under the curve, like all that happens is loss of information. So if the raw data would be available, then the problem would be solved, but you can just stick this into your objective function.
Yeah.
But because the raw data is not...
No, because this is the gut appearance that we learn. It's not a system where we have data for. So this specifically works very well if you don't have the data for the curve that you're learning specifically. So the data that we have is dependent on the curve that we're learning, but we don't have data directly for this curve.
It is possible to measure it, but it's extremely expensive. You need to use stabilized strip tracers. So it is possible, and this is how the equation that Max showed initially was validated, but it's too expensive to deploy this as a standard measurement. It's really hundreds of thousands of euro per test. It's a very expensive measurement. So we usually infer it, or indeed apply these constraints based on what we know from these tracer studies. But there is variability per person.
I was more thinking about it like 2 hours ago when we saw, I think it was the area under the curve of the glucose response.
Mm-hmm.
Yeah, but so over here it's not the area under the curve of the glucose response, but the area under the curve of the gut glucose appearance.
Yep.
Okay, yeah, that's a different.
It's glucose appearance in the gut, so it's something we can't directly measure, but we know how much glucose was in the meal, and we know from literature that this should appear within, I think for glucose it's, for a liquid meal it's 2 hours, for a solid meal it's 4 hours, so we can apply indeed this more qualitative information to at least ensure that all of it should appear and the window at which it should appear. But indeed directly measuring it is possible, but very expensive, so it's not usually done. Anything else? If not, we'll be marginally early lunch break. I think if you do have any questions or want to contact us for any follow-up, these are our contact information, and indeed Max has his GitHub repository up there, so a lot of what we discussed today is already available in public repositories, the code accompanying his preprint, but also these workshop repositories are publicly available, including the previous one with the Jupyter notebooks that I think if you're less familiar with these topics might be a little bit more easy to follow because the models are more general. You don't need a detailed knowledge of endogenous glucose production to understand what we're trying to do. So thank you all very much, and also for some of your suggestions and feedback. I think for us this has been really useful. So thank you.
Thank you.
Thank you very much, Michelle. And indeed, if there was anyone